So since I stand between you and the end of NANOG, I won't keep you here for much long. So this talk is about how we can use Google for doing networking research. And the title of the talk is Unconstrained Profiling of Internet Endpoints, that is IP addresses, via publicly available information, as in on the web. This is joint work done with Yonath. He is a second-year graduate student at Northwestern University. And myself, Soups Ranjan. So I am with NARAS, and this work was done with, in collaboration with Alexander Kuzmanovic, who is Yonath's advisor at Northwestern, and Antonio Nucci, the CTO at NARAS. So as I said, is it possible to use Google for doing networking research? That is, can we, if we wanted to find out more information about an IP address, could we just send a Google query for it, and could we learn something about it? As it turns out, whenever you get a chance to try it out, you will find tons of information about IP addresses are already available on the web. Now the question is, can we do this in a systematic way so that the results that we get, they are more structured? And that is the question that we try to address in this work. Oops. So, and one of the other applications for this would be, for example, if you have a security portal via which you are monitoring for DDoS attacks in a security operations center, and you see a DDoS attack and you see the IP addresses which are launching the attack, then one of the first questions which could come to your mind is, what have these IP addresses done in the past? Are these bots, or are these actual human beings who are probably contributing to the DDoS attack? As we've seen in the past, there have been quite a few DDoS attacks. For instance, one which was recently launched against CNN, in which it was actually human beings who were clicking on CNN, refreshing the page continuously in order to potentially DDoS it. So now, as it turns out, one of the first things you would want to do is maybe do an NS lookup for that IP address, or you could do a whois query to find out what else has this IP address been doing in the past. Sometimes you may not get any information out of NS lookup or whois, and then you turn back to Google. And you would find tons of information which comes with both the URL and the hit text surrounding the IP address as found on the web pages. And now, as you would see, there are tons of keywords over here, such as stat. The most common one is stat and usage. Now, you would be thinking, and this is the question we try to address, how can we now make use of the results that we got out of Google for better understanding what this IP address has been doing in the past on the internet? And the other question, the obvious question which you may have is, where does all this information come on a search engine? Where does it come from? So there are multiple ways. One of the ways is a lot of servers, for example, gaming servers, their IP addresses are listed on very well-known websites. Similarly, it turns out even you could learn a lot of information, not just about servers, but even about clients. And the way this happens is that a lot of websites, they run logging software, and sometimes their web logs are posted on the internet, and Google crawls it. And you could, in fact, if the web log contains the information, you could even find out, for example, what is the operating system that this IP address as a client was associated with, what is the web browser that the client accessed it with, and so on. Similarly, a lot of proxy services, they have the logs available on the web. And even P2P information is available on the internet, because the first point of contact, usually with a P2P swarm, is a publicly available IP address. For example, for BitTorrent, you typically go to a torrent portal and find out the list of torrent servers you could contact. And moreover, for a lot of ban lists, blacklists, and spam lists, they also have web interfaces. And even that information, it finds its way into all the search engines as they crawl the web. Now, what we wanted to do was to see if we could answer a couple of networking research questions. So one of the first ones we tried to answer was, can we use this information available on Google to get an idea for what kinds of applications are people using in which parts of the world? And can we, most importantly, can we do this without even having access to any traces from those countries? The second question we wanted to address was, can we use this information for classifying traffic, as in when we do have access to a trace and we see a packet from one IP address to another IP address, then can we make use of this information that we got from Google for better classifying this packet, as in which application it belongs to? There have been a lot of approaches for doing traffic classification, those which are behavior and statistics based and just look at the layer 4 information, some which the deep packet inspection utilities which go deeper and look at the layer 7 headers and payloads. However, we wanted to answer the question that, just by using layer 4 information, that is the port numbers and IP addresses, in conjunction with information available on the web, can you actually classify traffic? So now I will first present the methodology for the methodology that we developed for harnessing information out of Google and presenting it in a more structured format. So the first thing the first thing our tool does is, you give it an IP address, it goes and it queries it on Google, and Google returns a list of results with both the URL and the hit text, where the hit text is defined as all the text surrounding the IP address as found in the web page. Then one of the first things we do is we try to just take a look at the URL that was returned by Google and see if from the URL itself we can make sense for what kind of information does this web page contain about IP addresses. It turns out there are some very simple rules you could use. For example, a website like dnsserverlist.org, very evidently it contains information about lists of DNS servers. So therefore, if we find an IP address for which Google returns a result from dnsserverlist.org, very likely this IP address is a DNS server. And we have we define a mapping from a list of keywords to a class for the website. So for example, if a website contains the keyword blacklist, spam list, or block list, then very likely it contains information about blacklisted IP addresses. Similarly, if the website contains information about, it contains the keyword mail server, then very likely all the IP addresses mentioned there are mail servers. If it contains the word spam or dictionary attacker next to or very close to the keyword mail server, then this website also provides information about spammers. Now, it turns out that the very simple rule where you just take a look at the URL to identify what does this website provide you, it doesn't turn out to be very useful most of the time. And then what you have to do is take a look at the hit list. For example, this IP address in question, it returned this particular hit text, which is in Chinese. What we do then is we override on Google's translator, convert it into English, translate it into English, and then we build a cache. We try to see if this particular URL is returned as a result for many different IP addresses. And if this particular website returns results for a number of IP addresses greater than a certain threshold, then we say that this website contains some pertinent information about IP addresses. And we also, when in this website cache, we maintain a list of keywords which are commonly found on this web page. So in this instance, we see the keyword QQ server, it commonly occurs next to the IP address, and therefore we maintain that association that this website maintains or contains information about potential QQ servers. So now I've told you about how we classify websites which contain information about IP addresses. Now we make use of the way we classified a website to now classify an IP address. So in our example before, if this particular IP address, it returned the URL which contained information about QQ chat servers, we come up with a very simple rule saying that this IP address is very likely a QQ chat server. And some additional rules as shown here are, for example, if an IP address, for instance, is listed in a website which was classified as a DNS list website, then this IP address is a DNS server, and so on. Now, as I mentioned, one of the first things we wanted to do was answer the question as, can you predict what kinds of applications are people using in which parts of the world? Very often, to come up with some ground truths like this, you have to rely on having access to network traces. But very often than not, you don't actually have access to network traces. Then how do you answer such questions? So what we did was we took a couple of traces which we had access to from China, Brazil. We also took a sample netflow trace which we had access to from US, and we took as a strawman, we took France, for which we didn't use any trace, and we tried to see, just by Googling for IP addresses which are allocated or assigned to these countries, what kinds of information would we find? So we picked a sample of 200,000 IP addresses from each country, and we Googled them. We obtained their the keywords which classify those IP addresses, and then we came up with statistical histograms for saying what kind of applications are prevalent. So actually, I'll skip this slide and move on to the next. So one of the first results we found out is that MSN as a chat software is very popular in Brazil. And we also said, okay, let's now see how good is this result, because this result on the left, on the right, where we say UEP stands for our Unconstrained Endpoint Profiling Method. So our method found out that MSN as a chat client is more popular than Yahoo and any other chat clients in Brazil. We wanted to evaluate how good is our result, because this result on the right-hand side was obtained without using any traces. So then we said, okay, let's take a look at the packet trace we have access to. And the packet trace also gave us a similar result, that MSN is the most popular chat client. Of course, in terms of the second and the third, and even in terms of the order of popularity, the results are somewhat different. And there is a reason for it, because a packet trace, it gives you an information which is temporally constrained, whereas our method using unconstrained endpoint profiling, it is taking a look at what kinds of results do you get for IP addresses. So it has a better spatial coverage. However, it doesn't have that similar temporal constraints that the packet trace has. Therefore, the exact order may not always be the same, but we found, as I'll show through the next couple of slides, that in most of the cases, we were able to predict the most popular application just by Googling for those IP addresses belonging to that country. Similarly, Gnutella was found to be the most popular peer-to-peer client being used. In China, we found out that QQ as a chat service is very popular, and similar results were found from looking at the trace we had access to. Now, the second question we wanted to address was, can you actually use this information to even classify traffic? So the way we went about doing this is, we picked the top 5% of IP addresses belonging to the country which we were looking at, and we Googled for those IP addresses we came up with all the keywords or the tags which classify those IP addresses, and we maintained them in a cache. And now we replayed that trace, and whenever we see either the source or the destination IP address to belong to this tagged IP cache, then we classify that flow accordingly. And the classification rule we use is very simple. It is, if you see a packet going to a mail server, it is very likely a mail flow. If you see a packet going to a website, say YouTube, then it is very likely streaming media, and so on. So of course you would have questions as to how well would such a naive and simple classification rule perform? And the other question you would have is this approach scalable at all? And I'll answer the second question first, which is that this approach is scalable because, as it turns out, there are elephants present in traffic. There are top 5%. 5% of IP addresses, they contribute to 95% of traffic in any network. And we took a look at the 3 network traces that we had access to, and it turned out that this rule was true. So therefore, we realized that we don't need to go out and Google for all the IP addresses from the trace. We can just Google for the top 5% of the IP addresses. Then to answer the first question, that is, how well does this traffic classification perform? We compared it against a method which was presented at NANOG 35 called Blink, which is a method which works in the dark. That is, this approach, it doesn't take a look at the payload. It only takes a look at the layer 4 characteristics of the traffic, and it takes a look at, it uses a graphlets kind of approach where it tries to see the patterns and tries to identify the patterns of who is contacting whom at which port numbers. And we said, okay, let's compare with this method. And our approach, as I just described, is based on using information which is freely available on the web, and by constructing a database of endpoints. So here are, so we did this, we ran this experiment on all the traces we had access to. I'll present results here from one of the traces. So as you see, the total amount of traffic which was classified by our approach is almost twice as much as was classified by Blink. And if you did a category by category comparison, Blink did not even find a few categories like streaming, mail, FTP, and so on. And the reason being that that Blink is a method which relies on having a certain threshold. That is, if you see more than a certain number of IP addresses sending traffic on a particular port to a particular server, then you potentially classify it as of a particular type. And a lot of times, those thresholds would have to be dynamically adjusted, and they may not work as good. It may work on one trace, but may not work equally good with the similar thresholds in a different network with the different traffic characteristics. It turns out that our methodology using Googling the internet, it also provides better semantics. For example, not only can we detect P2P, not only can we detect, for example, chat traffic, we could even go ahead and classify it as an MSN flow or a Yahoo flow. And all of this without even taking a look at the payloads and without even taking a look at the port numbers. Now, the other question you might have is, how good does this method perform against a layer 7 signature-based traffic classification? Now, there are lots of deep packet inspection technologies which take a look at which take a look at strings or regular expressions in the layer 7 packet payloads and headers to identify and classify traffic. We compared against one such solution which NARS develops, and the signature-based solution is shown in red and UEP is shown in blue. And the main result is that Unconstrained endpoint profiling, it performs as well, almost as well as signature-based classification. UEP was able to classify 60% of traffic compared to the signature-based methodology, which classified 70% of traffic. So there are more details in the paper, but I would like to now point out that this method, it works equally well, or in fact even better, in cases where there is only sampled traffic available, because sometimes ISPs, they only consider it to be scalable to provide sampled flow information for traffic classification purposes. And typically packet sampling is deployed where you would randomly pick one packet out of every, let's say, 100 packets for a 1:100 sampling ratio. And it turns out one of the first questions we wanted to ask was, when you're working with sample traffic, then what kinds of IP addresses are still left in the traffic? So we took the traces we had access to, the packet traces. We implemented and emulated Cisco NetFlow packet sampling, varied the sampling rates, and as you see on the x-axis, I have the varied sampling rate going from 1:1 to 1:100. And we wanted to answer the question as to how many IP addresses are present in the trace. As you see, we did this for 2 traces we had access to. As you see, the total number of IP addresses that is left as you go on sampling, it reduces from it reduces to 20%. However, and most importantly, the top 5% of IP addresses, which contributed to 95% of the traffic, they still remain in the trace, even after you sample it all the way up to 1:100. And that result is important because it tells you that if you can go out and Google for those top 5% of IP addresses, then even in cases where you only have sampled net flow available, I don't know what happened here. So, but no, man, I'll just talk through the rest of this because I was almost at the end of the talk. So even in cases where you only have sample net flow data available, our unconstrained endpoint profiling based traffic classification, it performs as well. I'm afraid I won't be able to show you the results for it, but the results can be found in the paper. And so to conclude, this was one of those wacky ideas we had, that let's see if we can just Google for IP addresses and see if we can use this for answering a couple of questions. That is, can we predict or can we come up with some sort of ground truths about what kinds of applications are used in which parts of the world? And we showed you results about that. And the other question we had was, can you use this such an approach for even classifying traffic? And I showed you a couple of results about that. More details about this can be found at our paper, and the talk can be found online on the NANOG site, and there is a URL over there which pinpoints to where the paper can be downloaded. So that brings me to the end of the talk. If you have any questions, I'd be happy to take them. Cool, no questions. Thank you.